This narrated PowerPoint walks through the details for linear transformations of random variables. The algebra for discrete random variables will be featured here. The results are fairly intuitive, but we want to show you why things work out the way they do. We'll be using discrete random variables from the first unit of week 3 to illustrate the relationships for linear transformations of random variables. So what do we mean by a linear transformation of a random variable? The values of x are multiplied by a constant b, and then a constant a is added or subtracted to that product. Some linear transformations will have both a b and an a. Some of them will only involve multiplicative shifts or additive shifts, but in general we could have both. Here are some practical applications of these ideas to changes of measurement scale. When we convert measurements from pounds to kilograms, from inches to centimeters, or from degrees Fahrenheit to degrees C, we're carrying out a linear transformation of the variable we're studying. Averages and standard deviations should be equivalent information, whether we're talking about the weight as 120 pounds or 50 kilograms. It's the same relationship, but we want to show algebraically what happens to those averages and standard deviations that leads to this conclusion. There are also a number of theoretical applications of linear transformations of random variables that we will be needing in this week 4 material. When we talked about z-scores in week 1, we were actually centering and scaling values. Centering is subtracting off the mean, and scaling describes dividing by the standard deviation. So when we set up our z-score number line with the mean as the 0 point or center and the standard deviation of the natural measurement scale, we were really doing a linear transformation. So there are both practical reasons and foundational theoretical reasons to look at linear transformations. If we have a discrete random variable x and its distribution, and again this material is in the first part of week 3, what we have to do to talk about this random variable is list the possible values of x, x1, x2, x3, up to xk. This is a one like a binomial with a finite number of possible values. And then to complete the specification of the random variable, we need to specify the probabilities that correspond to these k values of x. So I've denoted those from p sub 1 to p sub k. If we make a linear transformation, we multiply every value by b and add the constant a, then this new random variable a plus bx has the set of values a plus bx1, a plus bx2, up to a plus bxk, and the probabilities just directly transfer over from the values of x. If you remember math, what we've really done in the linear transformation could be described as a one-to-one transformation. So the probability for a plus bx1, that value has the probability p1 associated with x1, and so on. So there's the probability distribution of our new random variable a plus bx. So a question that we want to look at: what is the mean of this new random variable? What are we going to do to get this? Well, practicing the definitions for discrete random variables, the mean of a plus bx is just going to be a sum of the values p sub I times a plus bxi. That's just an application of the definition of the mean of a discrete random variable. By the algebra of summation, we can break apart the term a plus bxi into its two components, and then we can write the sum as the sum of p sub I times a plus the sum of p sub I times bxi. It's just the good old distributive law at work here. Now we can go to work on each of those terms in the summation separately. So what we're going to do with the first term is pull the constant a out of the summation. It doesn't have any subscript I, so we can write the sum of the p sub I times a as just a times the sum of p sub I. And we can do the same sort of algebra on the second summation. Again, the b is a constant, so it can be written as multiplying the sum of the p sub I x sub I by b once. Now if we take a look at what we've written here, one of the things we're going to do at this point essentially is some recognition. By definition, the sum of the probabilities from 1 to k over all the possibilities of our random variable has to be 1. And if you look at the summation of the p sub I x sub I terms, that is going to be the expected value of the original random variable x. So what we have at this point is a times 1 plus b times the expected value of x. For a practical example, the mean in kilograms is just the mean in pounds divided by the conversion factor 2.2. So the intuition that the mean being 120 pounds is exactly equivalent to the mean being 50 kilograms is justified by the algebra we've looked at with the summations. Often standard deviations and variances are a little trickier. We really need to work on the variance scale first. So we'll ask, what is the variance of our new random variable a plus bx? And again, we'll work with the definition to write this out. The variance of any random variable is a probability weighted sum of the values of the random variable minus the mean, and then that difference is squared and we weight by the probabilities. So again, we're going to use algebra on the summation and see how we can simplify it. So what we're going to have is the subtraction a minus the expected value of a is just going to be 0, and then we're going to have b sub I times both x sub I and the expected value of x sub I. And I've tried to use square brackets and curly brackets to make it a little easier to see what's going on. Both the b and the x sub I minus the expected value of x sub I term are squared, but we're going to work with that in a minute. B is still a constant here, so it can be pulled out to multiplying ahead of the summation, and when we do that, what happens is we actually have the constant b squared. So now we have b squared times the sum p sub I times xi minus its expected value squared, and again, almost by recognition of the formulas, this is b squared times the variance of x. So that's what happens on the variance scale. Nothing changes with the a because we're just shifting back and forth, but we actually have the constant b squared. But when we take the standard deviation, square root of the variance, very strictly technically, I have to write the absolute value of b. Most transformations will have positive constants, but we could have a negative one, and then of course when we take the square root of b squared, we're always going to get a positive number, which is what that absolute value is doing there. So the standard deviation of our new random variable is just the absolute value of b times the standard deviation of x. Again, using our conversion with pounds and kilograms, the standard deviation in kilograms is just the standard deviation in pounds divided by 2.2. So here's a summary of what we've done. These are the results that we're going to use for the rest of the course. The mean is transformed in exactly the same way as the values of x. If we simply add a constant a to the values of x, basically what we're doing is we're shifting all the values by the same amount, and the shape of the distribution and the spread are unchanged. We saw that in the derivation with the variance on the previous slide. If we multiply the values of x by a constant that is greater than 0, then the standard deviation is multiplied by that constant b. We're going to have exactly the same results for continuous quantities. It's just that we'll need to work with integrals to define the mean and the variance. So I've left that kind of derivation for your future courses. So finally, we want to go back to the z-scores we introduced quite informally in week 1 and talk about z-scores as a very special case of linear transformations. This is important for continuous random variables, and we'll be using this a lot in our material for the rest of the course. What I'm saying here in this derivation holds whether we're working with a sample where we have the average x bar and the standard deviation s, or we're working with a population where the corresponding notation is mu for the mean and a sigma for the standard deviation. We're going to have exactly the same sorts of relationships. So basically, as I mentioned, centering is subtracting off the average or the mean, scaling is dividing by the standard deviation. So this is what it looks like for z-scores if we translate into the notation for constants that we've used here. So when we center, we're making a linear transformation a plus x with a equal to minus mu to line up the algebra. And so what this gives is the expected value of x minus mu equals the expected value of x minus mu without the expectation sign, because the expected value of a constant is just equal to that constant itself. And then putting all the notation together, e of x and mu are two alternate notations for the same thing, so that difference is going to be 0. So when we center a random variable, the new random variable has mean 0. Okay, there it is back again, sorry. When we scale by dividing by the standard deviation, this is also a linear transformation with a constant b equal to 1 over the sigma using the notation for a population. And then what happens here is the standard deviation of the new random variable, 1 over sigma times the quantity x minus mu, is just 1 over sigma times the standard deviation of x minus mu, and then the subtracting off the mean, doesn't change the variability of x, it just shifts the values up or down. So what we have is the standard deviation of this centered and scaled random variable is equal to 1 over sigma times sigma, which clearly works out to 1. So again, we introduced these ideas rather informally at the start of the course in descriptive statistics, and now we have tied this to a very special linear transformation of a random variable. The importance of centering and scaling we've already seen in our week 3 work with the normal curve, that the centered value has mean 0 and the scaled version has standard deviation 1.